Okay, so welcome back. This is part 3 in our series where we are helping you to develop your software engineering and design skills. And we're using a real world example that highlights the fact that in the real world, if you're going to develop software, you're going to design software solutions. The tough part is figuring out how to design a solution, how to engineer the solution, and then using whatever tools at hand is usually the easy part. So this challenge was to find an algorithm, a solution to a real-world design problem, engineering design problem. And it is what you see here, where we've got as input, we've got some pairs of numbers. And those pairs of numbers defined a real-world configuration of the electric power system that feeds your home, your city, your state. And I want to take all of this data and I want to draw a diagram so that we can see visually how the electric power system is configured. And then in the next steps, what we're going to do is show you how to develop a methodology to solve the power flows and voltages and so on in the power system and display them on this diagram. And this challenge was to do one part of that, which is to take that input data and automatically, independent of the data, figure out a way to draw this diagram representing the electric power system. Now again, we have these vertical lines are buses, which are real world, what are called electrical substations, and the horizontal lines are the lines with the power flowing between these substation buses. And you've probably seen these lines up here on the left. These are the electric power lines feeding power from the utility. And on the bottom right here are the electrical substations, and we're simulating just the buses, which is where the power lines come in. And connected to those buses are circuit breakers and transformers and so on that take that power coming in and distribute it out to you and your neighbors and your city and so on. These are actual real-world pieces of equipment that we're simulating. And our challenge was to take the input data describing that configuration and to draw a diagram. Now, a few weeks I started with this series, and we've been talking about how we might approach that. What are some skills we need to figure out how to approach this problem, which turns out to be a fairly complex issue, which I presume is why I've got so few views. And in the last few weeks, I've only got like 100 views. And I also had somebody downvote my 2 videos, presumably the same person who, I guess, found out that they had no clue how to solve this, so they got upset and ran away to play video games. But anyway, we're going to, in this video, take the next step, take all of the design criteria that we've developed so far and try to figure out how to take all of that design data and convert it into what are called data structures that we can use in our software that will allow us to access the important data that we will need to figure out where to place all these lines and buses on the diagram. And ultimately, we're going to be developing this C# Visual Studio Windows Forms application that takes in the data and gives you some feedback here, and ultimately will design and draw this diagram independent of the input data. So as we talked about before, we identified some constraints, and we made our own constraints and decided that we are going to develop a grid that defines the locations of the lines and buses in our diagram. And that grid is going to vary depending on the input data, but here is a simple example of a grid that we're going to develop. And we are going to also define in that grid what are called columns. And we need columns to define where we are going to place our buses, our vertical lines. And each column is going to have inside of it positions, which represent bus positions where we're going to draw the buses. So you can start to see we've got this column, we've got these subcomponents of positions that we can fill with buses. And we can also have adjacent positions. If we need a long bus, we can have adjacent positions filled. And we're also going to define lanes in this grid. And the lanes are going to define where the lines are drawn. And these are going to be drawn in these individual blocks. So you can start to see the data structures we can implement here. We're going to have columns with sub positions and then lanes with blocks. And those are going to allow us to define the buses and the lines and how they are laid out. So now we can access, if we have to place a bus or a line, we can now access a specific location, find out if it's occupied, and if not, we can draw a line or a bus in that position. So now we've got data structures of a grid, we've got columns with sub-positions, lanes with blocks, and so on. So you can start to see how we're developing some data structures. And again, we're going to have in our columns, we're going to select a position, and we're going to, in that position, draw a bus. And then in a lane, in a block of that lane, we can draw a line. So now we're starting to make it a little bit easier for us to be able to access specific information. So we know that a grid is comprised of columns and lanes. Each grid component, which is a column or a lane, has properties and subcomponents. So for example, a column has positions, and each position is going to have a status, as we talked about before. For example, is that column position, is that occupied by a bus? So it's going to have an occupied status, and if it is occupied, we probably want to have a bus number associated with that. So you can see we've got a column and then a subposition and then properties, occupied, and also a bus number. But also keep in mind, we're going to have to draw those lines when we draw the diagram. So each column position is also going to have info on how to draw a line representing a bus. So it's going to have graphical pixel locations and dimensions. So we're starting to see there's a lot of data here that we need to represent in various data structures. And the same thing goes for the lanes. We're going to have blocks comprising each lane, and the occupied status of those blocks is going to have to be included. And if it is occupied, we're going to have to identify what line is in that block, like a from bus and a to bus. And again, as with the columns, we're going to have graphical or pixel locations and dimensions. So you can see there's a lot of data here. We're going to have to define some structures and figure out how to put all that data together. Now, there's also other considerations in our design. If we're going to do this right, if we're going to engineer this correctly, we're going to have an eye towards, hey, what if we want to modify this in the future? So, for example, does this design allow for easy implementation of other new features? So, for example, if you know anything about substations in the real engineering world, we are representing just these lines coming in, but there's also components inside of this substation that we may want to represent in the future, like circuit breakers, transformers, generators, and so on. So if you know about the real world, you may say, hey, wait a minute, I'm just drawing buses, but maybe in the future we're going to have someone say, hey, we need to also represent some other components. So we have to know something about the real world and say, hey, maybe we want to allow for future modification to add other types of components to the buses, not just lines. So that's where the engineering world has to be part of your view, rather than just what language I use and whether I use a for loop or not, right? Also, we need to consider optimization. Here we're developing some structures and substructures, but is this going to be the most efficient way to do it? Can the design be simplified and optimized? Also, is this an intuitive approach? So is it easy to understand, modify, and debug? You know, your software is going to be around for years, and if somebody looks at it in 2 years, says, what the heck are these guys doing? Probably not good. So you want to make sure that you are reviewing this in terms of future modification, optimization, debugging, and so on. So now that we've got these structures kind of defined, we're going to need to, for example, if we want to place a bus in this particular column and position, we're going to need to have information about if we want to extend this bus, determining whether these blocks below it are occupied, because if they are, we can't extend the bus. But now that we have these structures defined, if we have occupied properties in all these, we should be able to access those fairly easily. So let's look at the possible data structures. We could define classes, like for example, our entire grid could be a class that has sub-objects of columns and lanes, and each column has positions in it, and each lane has blocks. And of course, those positions and blocks are going to have properties. So we can start to see that we might have classes that define grids, columns, position, lanes, and blocks. And then the grid will be laid out as maybe a list of columns and a list of lanes, where each column and lane is a class. And then since we have to keep in mind that this grid can grow and shrink as we process the data, so it's nice if we have lists, because then we can add and remove from the list as the grid size changes. So why would we choose classes? Well, classes, as you know, have properties and they also have methods. And we're going to have properties like occupied status, the bus or the line number, the graphics data so we can draw the component. But also we might need methods. Like for the column, we're also going to have to draw a bus in a certain position. And for a lane, we're going to have to, for each block, draw a line if it's occupied. So we can start to see we might have some methods and properties, which is why classes might be a really good way to approach this. But again, we're going to have all these data structures. And once we have those, we're going to have to access the information when we're doing our algorithm to place lines and buses. We're going to have to access that data to make sure that we can do our line and bus placement. So at this point, we have defined basically the rules, the design rules, the criteria that we're going to use. We started to look at the actual algorithm we can use to determine where we're going to place our buses and lines. And we also have defined the data structures where we can actually get the data. When we do the algorithm, we're going to have to find out, hey, is this column position, is this occupied? So we've already defined that. So now what we can do is we can focus on implementing our algorithm for placing lines and buses based on the design rules, the criteria, the constraints, and also accessing data from these data structures. And in the next video, we'll start to implement some of that, and we'll start to look at developing those classes with the properties and methods, and also implementing the algorithm based on those data structures. So if you're liking these videos, I encourage you to hit the like button, subscribe, hit the bell notification, but most of all, please let others know that we're here so we get some views. Really appreciate it. Otherwise, take care. Have a really good day. Thanks.